Hey, oh, we got a question already. 44. I'm keeping the channel on 44 unless something disrupts it. I was not going to count them because I hear the bookstore still keeps running out. Yeah. I intend to ask you some questions, but don't worry about it. Play along in your head. Thank you. I won't lie, it's still bad, but remarkably better at this point than I thought I would be. I thought I was still going to be super swollen and nothing but crutches at this point, and I hobble around home fairly well. If I'm out, I got the crutches because they act as a crutch. Yeah. Do you have to have? It's probably the typical answer. I'm following the 11th. I like the 11th, so I'm holding you to anything that's in the 11th. However, the 10th shouldn't be that much different. The content is pretty much the same, but questions and things. So if I refer to numbers or problems or check your understandings part, you might not have them, or they might be a different chapter. But I expect the content is very similar, so you probably will be safe with that. My disclaimer is, if I do refer to anything, I hold you to what I'm referring to. But the homework, since it's online, they come from this author mostly. I usually adjust them, make my own answers or solutions, but I get most all the ideas are from him, which are quite. If you haven't realized, a lot of the questions he asks in the back of the chapter, those are available to be drawn from online, so sometimes that question could be right from the text. You'd only know if you looked them all up. So, some people have asked me about an ebook, if that was okay. Sure, it's the same content, so it doesn't bother me.
So the common story is out of clickers?
Yes, it's out of clickers.
Yeah, we can't get them anymore.
Right, we just covered that three minutes ago. So keep trying to get it, but I won't hold it against you yet. So, on that vein, I've been receiving lots of emails, which is fine. I answer them, but 80% of the questions I've been answering in emails have been answered in class multiple times, or on the syllabus and in the lecture videos that you can rewatch. Sometimes it's easier just to ask me. I know, so I answer you. Just so you're aware, if other questions come up, the answer might already be posted. I also appreciate, I kept checking Sunday every few hours to see if there was a message. Okay, who's cramming their homework since it was due Sunday night? And I didn't get any messages. So that either means you forgot, you blew it off, you didn't have any questions, or you did it earlier to make sure things were going to work out. So thank you. I can tell the majority of you did. I appreciate that. Do you have any questions about the homework? Because in theory, as of now, you can see the answers. Of course, I'm sure you haven't looked yet, but you guys went through it. Is there anything you wanted to ask me at this point about those?
Yeah, in the instant where they're, I can't remember what the question is, but
I have it in front of me, so maybe we...
I think it was 5. Is where they throw the ball up in the air, asking, does it ever hit a point of mechanical equilibrium?
And you put?
I put it does.
Where the heck? Where'd that one go?
But I'm still not wrapping my head around that. Isn't there some point that it does stop? There's got to be like a fraction of a second where it's just neutral or just equal.
Oh, I guess I was thinking that one had a picture. Guess it doesn't have a picture. There it is. I think number 8. When a ball is tossed straight up, it momentarily comes to a stop at the top of its path. Is it in equilibrium during this brief moment? So now we're all on the same wavelength. And your gut was, remind me again.
Corey, that it
Corey.
would eventually be at some point of
Okay.
equilibrium.
I'll back up before I answer. Let's define what is this mechanical equilibrium. What are some things we know about it or have to be true for it to be in mechanical equilibrium? Because that'll help us answer this. The net force would be zero, which also tells us if there's more than one force, they are canceling each other out. Yes, so there's no net force. No, yeah, okay.
Would it also mean that the acceleration is constant?
It also means the acceleration.
Or the acceleration is zero, sorry.
So technically you're right, zero is constant. But yes, more accurately it would be zero, because if there is no net force, there's no net acceleration, which is chapter 4, Newton's second law, and we're almost there. If I don't start into it at the end of this lecture, it'll be next lecture. So, with all those things in mind, it means, what does that mean if all those things are happening? Is the motion changing? Do we have a change in motion? What's Newton's first law?
Law of inertia.
Law of inertia, and that's state, there's like kind of two halves. Things at rest want to stay at rest, and things in motion want to stay in motion, unless acted on by an external force, and more specifically, an external net force. So if there is no net force, there's no net acceleration, there's nothing trying to cause that object to change its motion, its current state of motion. So if it's at rest, it'll stay at rest, and if it's already moving at a certain speed, it'll stay moving at that speed. There's nothing to cause it to change its motion. So mechanical equilibrium does mean no change in motion. Doesn't mean it cannot be moving. It just means it's not going to change its motion. Do you follow that? I see some heads or something. I'm not seeing heads. So that was the 85 miles an hour in the car. There's forces acting on the car, but there's no net force because you're not accelerating or decelerating. That's just a direction. And so you don't change your motion. You just maintain the current speed you're at until or unless something does act on it. Thus, back to the problem. It's not in mechanical equilibrium because what is always acting on it? When you throw an object up in the air, what's always acting on it? Gravity. On its way up, it's being pulled in which direction? Down. So it's trying to accelerate downward, but it's moving up. So it slows down, and it's tricky. This is why we ask these questions, to cover these points, because everybody that doesn't take a physics class thinks that, it comes to a stop and everything's hunky-dory for that brief moment. But why does it start falling back down again? Because gravity's constantly acting on it, on the way up, at the top, and on the way back down. And the acceleration due to gravity is? Very good with the units. Yes, 9.8 meters per second squared. So it's always trying to be accelerated downward. Thus, there's always an acceleration. There must be a net force on it. It's never in mechanical equilibrium. Does that explain it?
Yes.
However,
No, it does. I'm still trapped my head around.
yeah, you think, what does go to zero at the top? Speed. It does stop its motion for a moment, but it's still in a change of motion. It went from moving up, stops, to turning around and coming back down. So it's in change. That's because it's being accelerated. There is that force acting on it. It's causing the change. But for that brief moment, it stops moving, and the speed is zero, but not the acceleration. They're different things. Yes?
So what would we call that force, the force that we use to, push it upwards, throw it upwards?
The force to throw it up in the first place?
Yeah. So is there a name for that kind of force?
No fancy name. A push.
Okay, so if the push force, it's, as it's going up, would it be correct to say it's decreasing or is it the same?
While I'm throwing this?
Well, when you throw it, obviously it's at the highest, you're applying the highest force, but as it's going up, isn't the net force on it, net force upward or force upwards decreasing because of the gravity?
I'm glad you brought that up. Isn't the upward force decreasing? Let's walk through it to explain it, because it makes me think of something else too. All right. It's motion. It's at rest. Is it in mechanical equilibrium? Are there forces acting on it? Yeah, which two? Yeah, it's weight down, and we call the upward one support force, or a normal force from my hand. They're balanced, no net force, no net acceleration, no change in motion. To get this to start moving, I want to change its motion, to accelerate. I have to push it. So my support force is going to increase. I push it. And that's going to be larger than its weight. And so that'll get it up to a certain speed, and then I let go of it. So it's in motion upwards. Once I let go of it, what forces are acting on it? Its weight still acts. Good, we just discussed that. But my support force is now gone. So while I'm pushing it, my support force for most people generally increases. I'm trying to... Actually, everybody's different how you throw it. But let me explain it. I mean, you could push hard and then soft and then hard, but you're moving it up. Here's my hand. Here's the car. Yeah, whatever. Okay. This is up. All I need to do is just supply a constant force. That's enough to get this thing to accelerate up to a certain speed. But I could make less force, a little larger force, blah, blah, blah. Let's call it an average force then. Basically, I'm moving it up by applying a force. And that doesn't have to change, but it could, depending on how you throw it. What that does, though, is that gets that up to a certain speed. It now has a certain velocity up. And so it's hard to say whether that's increasing or decreasing. The force that's acting on it now, only, I shouldn't mix, is its weight. Remember, due to its mass times gravity, the acceleration due to gravity. And does that change? Does this guy's mass change? Does the acceleration due to gravity change? So his weight never changes. So the same force acts on it on the way up, at the top, and back down. So you can't say this force is decreasing or increasing. It's constant. It's its weight. Gravity's constantly pulling down on it the whole time. Now just turn this around. It makes more sense, it seems like, if you were like in a cart or something. And something's trying to come at you, right? And you push on it and make it go back the other way. So while it's coming at you, you're slowing it down, but it takes a moment. You stop it, and you push it back. You're applying a constant force the whole time. You push on it, still pushing, still pushing, still pushing, still pushing. That's like gravity. It's the same force. It's not changing. It just changes its motion. It was moving this way, slows down, stops. Now it's not moving at all. It turns back around and goes that way. How are we doing? How do you feel? Tell me. Is this confusing? So cool. Yes? You had a question earlier.
I can never get this right. If you're trying to push something, does it say it pushes back with an equal force? So how do you ever get anything to move?
Excellent. Good. Because this...
I've never gotten this.
Good reasoning, though. You're thinking like a scientist now, though. If you push on something to try to get it to move, wait a minute, it pushes back on you with an equal and opposite force. This is Newton's third law, which we haven't gotten to yet. But yeah, wait, if they're equal and opposite, they cancel. Shouldn't we be in mechanical equilibrium? Shouldn't there be no motion at all? I mean, that seems logical, right? That's your conundrum. Who else has thought that? Raise your hand, let's see. Admit it. Yeah, see, there's other people. The catch there is when you want to determine the motion of an object, the only things that are going to affect the motion of this object are the forces on the object. So if I push on this, that'll affect the object. There is that equal and opposite force pushing back, but what's it pushing on? I push on the truck, so the truck pushes on me, my hand, the skin. You're right. So that's going to affect my motion. How many of you will jump to it, shot a gun? Because I think it's the most, it helps you for recoil. So we're not to Newton's third law yet, but you shoot a gun, what happens? You get thrown back, you recoil. That's because the gun exerts a force on the bullet to accelerate it that way. But Newton's third law says that the bullet exerts an equal but opposite in direction force back on you and the gun. That's why you feel it. So yeah, they're always come in pairs. That's how I do Newton's third law. All forces come in pairs. But they have to act on different bodies. If you push on something, that something is pushing back on you. And so it's trying to affect two different objects. Does that help?
Yeah, so you're saying what's happened is your hand doesn't move.
It feels a force, but how it changes its motion is based on its mass.
Right, but when you push on with your hand, the equal is there, so your hand doesn't move the truck.
Yeah. Let's do an extreme example as I hobble over here. I push on the wall. Wow.
That'll sound good.
Sorry. So you push on the wall, it's pushing back on me. When you have a collision with your car, it's going to crumple your car, right? So it seems to have more effect on you. Why? You know the answer to this already. Why does it affect the car or me more than the wall, generally? What's that? Difference in mass. Mass is a measurement of what? How much matter we have. Yeah, and Newton described it as a measurement of what else? The I word. Inertia. How do you define inertia? Resistance to change. So something with less mass is affected more. It has less resistance to change its motion. And so puny me in a car would be affected more by that force. It's the same force between the two, one on it, one on me, but I'm smaller. So I have less inertia. I'm affected more. So with a hand, we usually don't notice it. But there's still that force there. Yeah, good observations.
So is that why in the question in the homework when it said, how much can a strongman lift, it's how much his weight is?
Yes, the strongman question. He's lifting a weight. Yeah, he can't lift any more than his own weight.
So if it's like 1 pound less than he can lift that, it's equal to him. He's not going to lift it. It's 1 pound more.
Yeah, more or less, it doesn't work. The cutoff is the equal. Yeah, you should try it. I mean, just find something. And you're just trying to lift yourself up, right? If the thing's fixed, how much force is required for you to exert to lift your own self?
At least as much as you weigh.
At least as much as you weigh, because the weight's down, right? So you need an upward force of at least that to balance it. If this thing can move, because it's on a pulley, you're just going to be pulling it down beyond that, right? You can't pull any harder than your weight is in that situation with that pulley.
Like that's why when you're a kid, you can do like 30 push-ups or pull-ups. You don't really weigh anything, and then when you become more like an adult.
Yeah, the bigger you get, push-ups are harder because you have more mass.
Yeah.
Hopefully you have more muscles by then too, but it's usually not, they don't grow at the same rate. Yeah, proportionally. There's a question in the back.
So how would something like hydraulic force have an impact on mass?
Hydraulic what have on mass?
Force, so like, say you got a hydraulic hammer, and the hydraulic hammer, it's the fact that it's hydraulic doesn't have an impact on its mass, but it could be then a lot stronger than just a manual hammer.
Well, the hydraulic uses an increase in pressure inside the hammer to move the... Okay, so it has to exert a force on the head to move it. It's dealing with its mass. But yeah, when you hit a nail, let's say, it exerts a force on the nail, little mass, so it's affected more. But the nail does exert an equal and opposite force back on the hammer head. But relative to the nail, the hammer head is quite massive. And so it has less effect on the hammer for that same force. So the hydraulic is real just, it can add the force you can exert to the nail than just a normal hammer. Because normal hammer is how fast you can swing it. Where this, it can do more than we typically can do in the first place. So that's the amount of force exerted. But correct. But if you can exert more force with a hydraulic hammer, that's the force between it and the nail. They come in pairs. The nail can feel more. It's a more effective hammer. Good. But the flip side is the nail is pushing back on the hammer with more force also. So you probably feel it more with a hydraulic hammer, I would assume. I've never actually used one. Do you know? Do you use one?
Yeah, I guess, but then hydraulic hammers usually weigh a lot more.
They usually weigh more. And now you know why. Because that kickback, it wants to resist that change of motion, so they have more inertia. Were you here for the lead lecture? When I hit the lead brick? It's that idea. Cool. Hey, this is good. This is good. You go.
Why can an ant lift more than its weight?
Why can an ant lift more than its own weight? Well, the strongman thing was on a pulley. There was a hanging weight over here. That'd be true for an ant too, if it was doing it in that situation. At one point I could lift more than my own weight. But that's just standing here, or something. With a pulley, though, I'm trying to pull up while gravity's pulling down. That's a different situation. The forces were up and down. When you try to lift something directly, I can push against the floor, and the floor can help support me.
Oh, okay.
So it's more just the way it's set up.
Okay.
So if an ant was doing the same thing as that strong man over with a pulley, he'd have the same problem.
Okay. All right, so this might be jumping a little bit ahead, but I've seen the term mechanical work being thrown around before. How would you define work?
We are going to cover work. Work is they usually say it's a form of energy. I like to say it's more of a way to transfer energy. Energy can come in different forms. You probably already know this. This is Chapter 7, by the way. We'll be there in a week or so. Potential energy, if you've heard of it, kinetic energy, gravitational energy. And there's energy of motion, energy of a compressed spring, and it changes forms and can be stored differently. Work is how it's transferred. It requires work to get it from here to here, or to increase it or to decrease it.
So like when you're pulling on the truck,
I'm exerting a force, but I'm exerting it for over a certain distance, which is actually what work is, how you'd find work, force times distance, since you know about it. Yeah. Power is another thing associated with it, and that's how fast you do something. You guys can understand it now. I'm not going to do it, but I can walk up the stairs like this, and I'm increasing my energy, something called potential energy. I've gained height. So I've gained some energy by doing work. But I did it at a certain rate. If I had walked all the way to the top, it'd take me a while. Now what if I ran? I've actually, from the bottom to the top, gained the exact same amount of energy. Because it's the same change in height. But which one do you think took more power? Running. It naturally makes more sense. You have to exert more and do more that way because you have to do it faster. So that's the rate at which you use work. We'll revisit that. But yeah, this all builds. That's why I'm making sure you understand this motion and force stuff.
One other question. I guess I wasn't clear on. It said if you doubled the guy's weight, the inertia would double. But didn't you say inertia is not a force? And I thought, well, it's a concept, so how do you quantify it? I guess the answer was, yeah, it would double.
Well, it's good. It's read it, if I can find it real fast. Which number that was. Was it the rock? Does a 2 kilogram rock have twice the mass? Was that the one?
Something like that.
Yeah. So does a 2 kilogram rock have twice the mass of a 1 kilogram rock? Yeah, kilogram's a unit of mass, so 2 is more than 1. Yeah. Does it have twice the inertia? Yes, because inertia is kind of a measurement of mass and that resistance to change. If you have twice as much mass, you will resist a change in motion by twice as much.
But you don't measure it. You can't measure it.
No, you can't measure it. Inertia is kind of vague that way. Mass is our way of quantifying inertia. It's all we got. Does it have twice the weight? It would, because it has twice the mass. So it's still being accelerated down, mg. So if you double that, then it will weigh twice as much also. Yes?
Can you define magnitude?
Magnitude is a value only. So 85, 62, 1.37827. And then it usually includes units, yes. But it could be for anything. So for force, we'd say 200 newtons. That's a magnitude. That's how big the force is, or little. 10 meters per second. That's a speed. Tells you how fast something's going. But that's only the magnitude. Things that only have magnitude we call scalars. Speed is a scalar, 10 meters per second. If we add what to it, it becomes a vector. Direction. So if we said 10 meters per second to the right, now it's a vector because it has direction and magnitude.
So then mass is a scalar?
That's right. Mass is a scalar. Force would be a what? Vector. Because it depends on which way you're pushing. How about acceleration? Vector. Up or down, right? It matters, yeah. Go ahead.
I was wondering how we got to the value 9.8 because, I mean, on Earth it seems like in different places, depending on the altitude or acceleration, it might vary.
It does vary a little bit, the acceleration due to gravity, but not much different from 9.8. Like if you're up on a tall mountain, it might be 9.7998 or down see this 9.812. I don't know, I'm making it up. So it doesn't vary much in our everyday lives here on the surface, so 9.8 is accurate enough. Do you want to know where they actually got that number? Or well, briefly. It's a force, and it was Newton. They used this something called a universal gravitational constant, which they figured out by doing a bunch of experiments, and this is what the number ended up being. Mass, and the distance between them squared. So if you have two bodies, two objects, they naturally attract each other because of gravity. And how strong that force is between them depends on the size of them and how far apart they are. So somebody figured out that that force is proportional. This is a term that means proportional to the masses. And it's also proportional to the inverse of the square of the distance. If you get farther apart, the force is less. And it's exactly equal if you throw in this constant value. Well, make one of these masses the Earth, which is essentially like doing this, and make this mass you. And you plug all that in with the radius of the Earth, and you get this value works out to be 9.8. You get the little mg. That's the distance between the objects. Radius of the Earth from the center to the surface where we all live. So that is why if you go higher up on a real high mountain, it does decrease, but not significantly for our purposes. But when you're doing important scientific experiments, you do have to take that into account. Never. You're always affected by gravity technically. So if you're out in space and there's no object near you anywhere, then the gravitational effect is pretty minimal. But it does decrease with distance, but it just slowly goes out to zero. So as the farther away we get from the Earth, we'll be pulled down by gravity less and less, and less and less. And at some point, it's essentially like nothing. But technically, two masses are still being attracted to each other. Thank you. I want to thank you. Of all the years I've ever taught, since '94, that was the most useful question-answer period, especially at the beginning of a semester, that any class has ever bothered. It's like they were too shy or too afraid to. I mean, this is your class. I want you to help you understand it. Besides, if you can't tell, I answer the questions, and I've taught you a lot of stuff I wanted to today anyway, if you didn't realize. So let's do some clicker questions and see if you understand some more. To you guessed or you connect?
Yeah.
You connect is working, you guessed is not.
Oh, it's usually the other way around.
But earlier this morning, you connect wasn't working, you guessed was working. So, they just like to shake things up.
Huh. Well. All right, those of you using ResponseWare and have it, there's the session ID number. It'll come up in a second again. It's over there on the bottom right. So channel 44 for clickers and session ID over here in the bottom right to log in. Now I'm curious, TLT, if I do presenter view in PowerPoint, which wasn't that, okay, good. Never mind. Answer my question. All right. You guys logged in? Here's the first question. Oh, yeah. See, we just discussed this, but I already planned to ask you it, so let's see if you were paying attention. Which one of these is not a vector? Speed, velocity, or force? Or maybe they're all vectors. Should be easy, so I'll give you 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. You all in? Okay. Okay, it didn't show up now. Okay, we're split, actually, pretty evenly. Some of you thought speed was not a vector. Why is speed not a vector? I'll give you that one. That's true.
There's no direction.
Yeah, speed does not include direction. What does include direction? Velocity. Thus, D isn't right either. All are vector quantities. No. Speed, it only has that magnitude. I'll admit I'm a little worried because I think I just said that. So, velocity and force, you guys answered me that those were vectors. So that's right. But speed does not include the direction. While I have this up, there's something I wanted to mention. Okay, you're in a car. How can you change your speed in a car? Give me something.
Push on the gas.
Push on the gas. You accelerate. Acceleration is a change of velocity. So you've just changed your velocity. Okay, how else? The brake. Good. That's accelerating. Everything I just said, but in the opposite direction, right? You're still moving forward. You're just accelerating backwards. Trying to change your velocity. Good. Anyway else? Not do anything. Okay, so if you let up the pedal, in theory, the resistance is going to be larger than your propelling force. And so there's a net force of bigger backwards. That would have an acceleration, change your motion. Good. Turning, the steering wheel. Does that change your velocity?
Yeah, because velocity is direction and speed, so you change your direction.
That's right. When you change your direction, you change your velocity. And if you're changing your velocity, you're accelerating. Can you do that at the same speed? Let's say you're going 85 miles an hour. Oh, let's slow down. You're a little safer. You're going 40 miles an hour, and you turn. But at 40 miles an hour, are you still changing your velocity? Yes. Are you changing your speed? No. So the magnitude stayed the same. You're not changing your speed. But you did change your direction, so the vector changed, velocity. And if you're changing your velocity, you're accelerating. Does that make sense? Acceleration is a change in velocity. And velocity, you can change the magnitude and or the direction. This one. All right, go. Space probe in remote outer space continues moving. And there's your options. Because some kind of force acts on it, or it continues moving in a curved path, or it'll keep moving even though no force acts on it, or it keeps moving due to gravity. What do you think? Space probe continues to move. Why? Or how? So if any of you are thinking to yourself, wow, you just keep repeating yourself. You're being redundant, Adam. I apologize to you. But that means good, you're getting it. But a lot of people, this takes multiple tries to sink in. We've discussed this concept exactly, even today, but applying it this way, so sometimes it just confuses folks, so I'm checking you. All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. Half of you think it's C. You are correct. But a significant of you thought A and D. So if something continues to move, it continues moving. That could be like taking that tennis ball and just chucking it out into space. And what will it do left to its own devices? Continue moving. Why? There's no net force on it. It'll keep moving in its current state of motion until or unless something acts on it, a force. So the answer was, even though no forces act on it. I'm just trying to emphasize, things can move without something pushing on it. Yes, you have to push on it to get it moving in the first place. But inertia, things in motion will continue in motion until some force acts on it to try to change that motion. Does that make sense? More nods. I need more response. Okay, good. Oh, come on. That one. All right, go. 10-Newton object is suspended by rest by 2 vertical strands of rope. What's the tension in each rope? 5, 10, or a little bit more or less? So you can picture someone hanging, or an object, 10-Newton object hanging from 2 ropes. What's the tension in each rope? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Bang. Oh, good. 86% thought B. So the majority are getting it. So not to make the others feel bad, but this is one where if you missed it and you don't understand what I'm getting ready to say, you got more to study. Or email me or something. So the idea is the object's 10. So that 10 newtons is a force in which direction? Down. It's the weight. So to balance, you need how much total up? 10 to balance. Well, you got 2 ropes supporting you. So each one only needs to hold 5. And then remember we talked about if you shift like this, this one's holding you up more. So will it be more or less than 5? More. But what will this one do? Less. What will the total still be? Good job. I had one more I wanted to do. This one. We started with this, so I hope we get it. The equilibrium rule that the sum of all the forces is 0 applies to what? Objects at rest? In uniform motion? Both or neither? I think we'll make it. All right, let's see who's responded. A little over half of you. 10, 9, 8, 7, 6, 5, 4, 3, 2. I can see some of you haven't voted yet. That's why I'm counting down so you know to get your answer in. One, somebody's not playing anymore. Okay. 85% for C. Bless you. Yeah. It can be at rest or in motion, constant motion. In either way, as long as it's not changing, because there's no net force acting on the thing to cause it to change. But it can be at rest or moving. Good. It will keep moving in a straight line if nothing's acting on it, no net force. If it's going to curve, that means something's pushing on it that way. So if you're going around in a circle, something's maintaining you, constantly pushing you inward. Yeah. So the Earth going around the sun is in a circle, right? So there's constantly an inward force keeping it turning. If we just got rid of the solar system, poof, and we're the only one left, then we'd start moving in a straight line, whichever way we were headed when things disappeared. Because that force is removed. And so we would just continue in our state of motion, whatever velocity we were at, in a straight line, until something else happens. A little weird to think about, huh? Okay. We're done. How do you prove we're not the center, but the sun is? There's a longer answer for that. But basically, briefly, it was done with observations and experiments. They would observe the heavens and try to come up with hypotheses, theories that would explain what they saw, why something's moving the way it's moving. And they had really complicated explanations for what they observed, still thinking we were the center. And it worked for them. That was the theory. It was right. It was well substantiated, and it explained what they saw. Now we know, though, we're not. And it's because of more observations that started disproving those. Those theories couldn't explain additional observations as we got better equipment and better telescopes. So we devised new theories or adjusted them, and they're holding strong.
Same question, but wouldn't that be very obvious because the sun it has a lot more mass?
Good. That means you understand this. It's more obvious to you and about everybody else that lives now. But to those that lived back, no, it wasn't obvious. That was the problem. Yeah, they didn't know. There's some things now or your kids are going to look back on and go, oh, that's obvious. And we thought it was something different. They'll think we're silly. Okay. We had an equation to guide our thinking. Acceleration is a change of velocity. And that takes a certain amount of time. You can rearrange that. If you want to figure out how much your velocity is going to change, then you just rewrite it like that. It's acceleration times time. Look at it this way with units. Acceleration is meters per second squared. Yes? Time is seconds. It's seconds. You can think of that as seconds over 1. Just to keep my fractions here. If you cancel some units, one of these seconds cancels one of these, and what are you left with? Meters per second. So it gives you velocity. So if you start from rest and accelerate at 9.8 meters per second squared for 1 second, how fast are you going at the end of that second? 9.8. Because you plug in 9.8 meters per second squared times 1 and you get 9.8. What if you were already going 20 meters per second? Let's say your initial velocity was 20 meters per second. And you accelerate at 9.8 meters per second squared for 1 second more. How fast will you be going now? That's right, 29.8. So you can also think of this as initial velocity plus this additional term. So it's how fast you're going in the first place. And you're happy maintaining that speed, right? You don't change. But then some net force comes along to help you accelerate for a certain amount of time. And you'll either increase speed or decrease, depending on which direction. So if you're already going 20, and you then accelerate 9.8 meters per second squared for 1 second, then you'll gain 9.8 meters per second of velocity on top of what you were already going. So this is a very useful formula. Equation to guide our thinking. So I wanted to share that with you. And this works in any direction. The examples I gave was vertical. So a lot of times people will just make this a g because it's the acceleration due to gravity. I mean, vertically, that's what it is. But it works horizontally as well, just with a generic a value. So with that, the last thing 5 minutes, see how we do. Want to make a table. It's in your textbook, but I find it useful. If you drop something, the distance something travels, how far it travels, depends on the acceleration also. So I want to make sure you have this. Just giving you this one. Basically, if you accelerate for a certain amount of time, then they found out that if you multiply it by this half constant, it'll tell you how far you went. And that works for anything. So if you start at a certain position and accelerate for yay long, you can know exactly how far away you'll be from where you started. This is especially helpful with dropping. So again, if we're dropping, we can turn that acceleration into gravity. And to make life easier right now, let's say g is 10. To make our math simpler right now. So, time, distance, and velocity. Okay. At time 0, you haven't moved and you're not moving. 1 second later. All right, let's start with, I hope, an easier one. How fast are you going after 1 second? Yeah, you're going 10 meters per second. Do you see why? Not as many head nods. How much your velocity changes? You're going 10 meters per second every second. 10 meters per second squared. 10 meters per second per second. So you're going to change 10 meters per second every second. So, 10. How about after the second, third, fourth? Because you're on a roll. 20, 30, 40. And these are instantaneous speeds, right? At that moment. After the fourth second, you're now going 40 meters per second. So if you jump off your roof and wait 4 seconds and haven't hit anything yet, you know how fast you're going. Because we know that acceleration. So distance. Well, how far would you have fallen in the first second? Good, you figured that out. A lot of people think you've fallen 10 meters because it's 10 meters per second. We're going 10 meters per second. We've fallen 10 meters. No. This is the funky thing. It works on this squared thing. And you have this half. So it throws things in that mess people up. If after 1 second you're now going 10 meters per second, what do you think the average velocity was? 5. The average of 10 and 0 is 5. What that means is if you fell at a constant velocity of 5 meters per second the whole time, how far would you have fallen? 5 meters. Or just plug it in if you don't want to think. But this is conceptual physics. So, how about after the second? How far have we fallen now? So you put in 10 here. And after 2 seconds, 2 squared is 4. 4 times 10 is 40. And half of 40 is 20. So I'm just plugging the values in there. Now we have fallen 20 meters. Anybody figured out 3 yet? 45, and 4 is 80. So, do you remember the fan cart I did with the little poker chips? The distance it traveled at the beginning were close together. But over here later, they got farther and farther apart. That's what happens when you drop something. It doesn't fall very far the first second because it's not going that fast yet. But as it picks up speed, each successive second, it falls further. Here it falls 15 meters in between. 25, 35, and the distance it changes increases. And Galileo is the one that figured that out. He did an experiment rolling balls down ramps, and he figured out that it was proportional to time squared. That's how we got this formula. Well, I'm not making you do that, but we just learn it now. So, any questions about that? Well, thanks. Been a good class. See you Wednesday.